Remember, different compression paths means different power inputs. So if you have, if you take an isothermal approach, if you take an adiabatic approach, if you take a polytropic approach, but also compressors have various different stages. So you have adiabatic stage and isothermal stage. Remember these, and I think this was the graph you have there is from the first lecture. So the amount of energy depending on the path you take to reach your pressure. For a reciprocating compression system, we can start with the shaft work equation, which is the volume multiplied by the change in pressure, the derivation, the integral between the P2 and P1 with the change in volume. Right? So your volume is constant, your pressure is changing, and the area under the curve at the compression is the compression stage. The amount of energy you consume, your shaft work is that area. So remember your PV diagrams. The smallest shaft power is the isothermal compression. So from B to C, remember your compressions, you have your A to B, B to C, C to D, or in this case, slightly different. And your largest power input is your adiabatic process, so your B to C. And polytropic is the middle amount of power. So polytropic means your compressor is cooling, but not cooling that much. Adiabatic means it's not doing any cooling, there is no heat transfer. Yeah. And that's important as soon as we move into a multi-stage compression. Single stages from P1 to P2, and you can reduce power by cooling, as I mentioned, so you effectively create a polytropic process, and hence it's a polytropic process. For low cooling rates within the casing, you can use a single compressor. But multi-stage compression allows you to have cooling just outside the compressor. So as soon as you compress something, it's going to heat up. It's going to become less efficient. So you compress it, it heats up, the pressure goes up. But as soon as it moves to the second compressor, it's at the temperature you don't want it to be, and the pressure is higher. And then to bring that temperature down, you're losing a lot of power. So what you do is you put two compressors, for example. You will compress at the first stage. You reach the pressure, a specific pressure, which is usually above the pressure you want. You move it to the cooling unit, so your intercooler. That cools the system down to the phase you want. So, for example, if the phase changes to gas or vapor liquid, you bring that down to liquid so you can compress again. Because if you put a vapor and liquid through a compressor, you're going to cause cavitation and your compressor will fall apart quite rapidly. So that's, I should have put the diagram up while explaining it. So you have your first stage, you have your cooling, intercooling, then you have your second stage, and that basically means it becomes more efficient. Now, you're not going to be calculating efficiencies or anything like that. Just remember that for the following years to come. As always, I have the hand signs. So at the first stage, you have your low pressure, and at the second stage, you have you intercool and you have a higher pressure, but the volume decreases, of course, because the volume of your gas is decreasing, so higher pressure. The reason that's important is when you come. The reason this is more efficient is if you use a single compressor, you're effectively trying to push this huge amount of gas. But that means your casing has to be able to withstand all that pressure. And the larger your casing, the more expensive, the more difficult it is to build a high pressure compressor. So if you build a compressor the size of this room, it's feasible. It's just going to cost you a lot of money because you need to make the walls extremely thick. Everything needs to be extremely thick, a lot of power to move things. So if you do it in stages, then because the volume of your gas decreases every time, you can build your compressor smaller and smaller and smaller. That's why you do multi-stage compression. So technically, it becomes cheaper rather than more expensive, which is something that is said in your notes. So it should become cheaper and more efficient rather than more expensive and complex. But physicists. So the design is simplified. You have various pressures that you can achieve. Remember, as I mentioned, your high pressure stage is smaller, your change in volume is smaller, so it's cheaper to design that compressor. That's something to take from here. With 3-stage compression, with 2 isobaric, so the graph you have is a 3-stage compression with 2 isobaric intercooling. You compress first from P1 to P2, you intercool. You move on, you compress again to P3, you achieve the temperature you want, and you move on to P4. So if you look at the solid blue line is isothermal, the blue dotted line is adiabatic, and the blue solid line is 3-stage compression. Now, you can see the amount of work done is the area within that graph, right? So if you go with adiabatic, no intercooling, the amount of shaft work you will do is significantly more than if you take a isothermal approach or intercooling. But isothermal is effectively impossible because you need to be cooling it. Every time you compress it heats up. And that's why your multi-stage approach is the most efficient approach, or the closest thing to an isothermal you can achieve. Yeah. So remember this graph, remember the amount of shaft work done. That doesn't mean you don't consume the required energy. Yeah. It's just your shaft work, the amount of energy you put within your compressor is lower. But you still need to use up the energy within your intercooler, but the intercooler is significantly more efficient than operating a piston effectively, because you lose a lot of energy throughout the compression, friction, and these kind of things. For the sake of this course, everything's ideal, but in reality, that's why it's more efficient. Remember that part as well. Multi-stage intercooling is less work. Just to put it into perspective, imagine going up this mountain and you go up straight. That's think of that as your adiabatic, or you go around the path all the way up. You still have to use up the energy. It's just easier and more efficient. So just to show you that graph again, you have your work done if you take a polytropic path. The adiabatic is even further out, and isothermal is the most efficient, but again, not really possible to achieve isothermal. With an ideal gas and a single-stage adiabatic compression, this is your shaft work equation. For P2 over P1, that is larger than 10 bar. I should say 10 bar. Sorry, that's not 10 bar. That should be the ratio. So if the ratio is more than 10 times the overall pressure, you need to split into 2 or more, depending on how big that ratio is. So from that equation, you can drive. Basically, you're splitting it between P2 over P1 and P3 over P2. So your gas enters your compressor, you compress it, so from P2 to P1, so your new pressure, and then intercooled goes to your second compressor, so it's a P2 going to P3, so P3 over P2. Yeah, it's just the same equation, just new pressures. Hopefully I've put the better equations up. So the total shaft work is the sum of the two expressions. So complete intercooling from stage 1 gas at the same temperature as entering stage 2. So you compress, you bring down the temperature, the same temperature and pressure enters your second compressor. So the total shaft work equals the summation of these two. So the pressure should be chosen to minimize the work done where possible. Now, I'm going to cover what's the best pressure for an ideal system, which is quite simple. So for an optimum intermediate pressure, you know the infinitesimal change in shaft work with respect to power over the infinitesimal change in pressure 2 equals 0, so slow compression. So if you expand that equation and continue expanding it, what you will get is P3 over P2 equals P2 over P1 is the most ideal temperature. Now, go through that so you know how to do it, but all you need to know for this course is P3 over P2 equals P2 over P1. The reasoning is, so that means the ideal pressure is the ideal pressure ratio is the same. So if you compress by 2 folds in the first compressor, the most optimum pressure for the second compressor is 2 folds as well. So from let's say from 1 bar to 2 bars, from 2 bars to 3 bars. That's what basically all that means. So simplified to RP1 equals RP2, so pressure ratio of the stages, stage 1 and 2. The minimum total work equals the pressure, so pressure stages are equal, as I mentioned. So the total pressure is RP equals P3 over P2. That's the pressure ratio for the whole thing. And extended, that means RP equals P3 over P1 multiplied by P2 over P2 equals P2 over P1 times P3 over P2. Which is the pressure ratios multiplied by each other. So the square root of your pressure ratio, it gives you the optimum pressure ratio. So if you have the two pressures, you take the square root, technically half it. If it's a square, then you get your pressure ratio. So put that in for your compressor designs, if you like, for your process design. I'm not sure if you're considering ideality or not, but you can definitely say for ideal situation that's the case. So with respect to the number of stages, that equation becomes basically n minus P2 over P1, and you continue the number of stages. So let's say 20 stages, again, same pressure ratios throughout. So RPI equals RP to the power 1 over n square root. For 2, 1 over n. Yeah. So I'm not sure what's wrong with these equations. So the total shaft work is related to the number of stages with compression stages. So gamma minus 1 over n to the n multiplied by gamma, the number of stages. So a number of stages is number of compressors. So your total equation effectively becomes n minus n RP, your pressure ratio, to the power gamma minus 1 over n gamma, which is, remember, your original equation just multiplied by n. Or you can just split it and do it stage by stage if you prefer. Yeah? And since you're doing programming in another course, that's basically it. So the overall pressure ratio is the total shaft work equals minus gamma. What is that? So that's great. RTN over gamma minus 1. So your PV. 1 minus P out over P in to the power gamma minus 1 over n gamma. Summary of intercooling. Benefits: you reduce pressure ratio per stage, you reduce the overall power input over a single stage device, reduce the gas and equipment temperature, and reduce the scope for chemical decomposition of both the gas and lubricant. So just to put that into perspective, Pressure ratio means you save a lot of money on compressor, large compressors. Also, it's a safety issue because the bigger your compressor, the bigger your compressions. If something goes wrong, the bigger the bang. And if you're around it, a piece of compressor will rip you apart. Simply put. It reduced the overall input power, so again, cost reduction, reduced the gas and equipment temperature. Now, as the temperature rises, again, it's a safety issue, but also the change in phase behavior. So all of a sudden, if you're compressing a gas or a gas and a liquid, if you change the phase, then you're going to have issues. Or with temperature rise, the pressure rises really rapidly, so controlling that pressure. And then you bring the temperature down to the desired temperature, all of a sudden you've lost most of your pressure. Yeah, PVT. Yeah, they're always related to each other. And you reduce the scope of chemical decomposition. This is more to do with fine chemicals, pharmaceuticals. So as soon as you increase that temperature, all of a sudden you can have decomposition. I think I mentioned to these guys the other day, I saw one of the engineers asking the same question on LinkedIn on why you would cool a compressor during startup for a specific pharmaceutical process. And one of the reasons you form gases because the temperature increases. But as soon as you form these gases, your compressor will start falling apart. And your chemicals start falling apart. So what you do is you cool it down. Now, thermodynamically, that is the reason, but I think the majority of engineers usually just say cavitation to prevent cavitation. But thermodynamically speaking, the reasoning is as soon as you compress, you heat it up. So when you heat up a chemical, you're going to have some form of reaction, some form of decomposition, or at least you will have some kind of physical problems. So increased temperature, increased pressure. Yeah. So the small volume of gas left during the discharge to prevent contact during stroke. So when you're compressing within a compressor, the real compressor, not the ones we're considering, your discharge valve opens a lot later. So imagine you have this compressor, your discharge valve in this course will open when your piston reaches all the way to the top. But in reality, your discharge valve will open when your piston is about here, so at that specific pressure, to release the pressure so the piston can go down. The reasoning behind that is if you have this piston compressing every time, hitting the top, it's going to rip the compressor into pieces. So remember that for your future designs. The gas trap is at the outlet pressure, and the theoretical volume is hence significantly above the actual volume. Now, remember, when you're increasing the size of compressors, the higher your compression rate, the harder it is to reach the very top, because your release valve will release a lot earlier, and then you have fatigue as well. So you need to consider that when you're determining the efficiency of your compressor. So your piston moves up, you release the gas. But the smaller your compressor, the higher the compression, the sooner this valve will open up. But also with fatigue, this volume will change. So the efficiency of your compressor changes over time. You need to consider these things when you're designing a process. Now, probably not at your level, but I'm telling you for future purposes. And also it's in your material, so I'm mentioning it. This is to prevent the compressor destroying itself. As the pressure increases, this clearance volume will increase. So the higher the pressure, the higher the clearance. One, for safety, and two, because it's more expensive to reach a higher compression, so you build more stages. Thank you, and we move on to tutorials now.